guys. Unified moles and stoic. We're going to do some balancing equations today.
That's MoNaCo over there. It's Milksy over here.
Yeah. Oh, I forgot that intro.
That's all right.
I was getting a little bored on it. So.
Well, it's all right. We still, you can variation a little bit. But
26 and 27. We're going to balance some equations.
woo, this is going to be fun.
This is what we like to do. It's actually one of the first things we do when we're doing stoichiometry in the lab is find the balanced equation to use.
Yes.
For all the other stuff that we had to do.
Yeah. A little footnote before we get into this. First off, it's going to take a little bit of practice.
Yep.
And second of all, for those of you little literal Larrys out there, there is an element of trial and error to this. So please do not get discouraged. We're going to teach you a process that will eventually work. Okay?
Yeah. So we got some nice transitions there. Spicy.
The law of conservation of matter states that matter cannot be created or destroyed, but I can simply rearrange some atoms. Okay?
Right. So a chemical reaction is, at its most basic conceptual core, I got a pile of these Legos over here.
Yep.
I'm going to do a chemical reaction and make this thing over here with the same pieces put in a different way.
Right, and I can't lose any pieces and I can't add any pieces.
Right.
That's really the basis of this. So,
all the atoms must be accounted for.
that's true.
And so the products and reactants become accurately predictable when we have a balanced equation. I can use ratios to say, well, hey, if you're going to put this much in of that reactant, I'm going to get this much out of this product.
Right, and I can actually accurately predict what the product will be chemically. Because you have to have the right numbers of oxygens and blah, 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 blah.
Well, we're going to be giving you reactions that have the reactants and products all outlined. You're just going to be putting in the correct mole coefficients to make them balanced.
Sure. Yeah, I'm thinking about that precipitate lab we do where we actually make you figure out the products.
Not going to do it.
It's coming.
I'm not doing it.
Oh,
Uh,
courage, Mr. MoNaCo.
There's no proof. It's all
Here.
It's black magic, that lab is.
Yeah. Here is an example of an unbalanced chemical reaction. Mr. MoNaCo, you want to tell me what you see wrong with this reaction?
Oh, yeah. Well, I have a different number of elements on the left-hand side of the arrow than I do on the right.
You're right. I see hydrogen and oxygen, two things forming one thing. So there's different things on either side.
Yeah, that's okay, though. I can combine elements to make new products.
Oh, I can.
But what I'm talking about is the fact that there are two hydrogens on the left.
Okay, so that's this.
Yep. There's two hydrogens on the right, and that's good.
All right, so we're good there.
But if you look at the left, you've got two oxygens
Yep.
and only one on the right. So
Problem.
something's missing on the right-hand side.
So that's
This reaction says I take two hydrogen atoms, combine them with two oxygen atoms, and it makes a molecule that contains two hydrogen and one oxygen.
And so one's missing.
An oxygen atom's missing. And according to the law of conservation of matter, that cannot happen here.
Where'd it go?
That's my point. Where did it go? We got to balance this. That's why it's an unbalanced
So
example.
this is what we're doing.
So, how to do these?
There you go. You doing the first one? Oh, we got some more stuff.
Yeah.
Okay. Balancing a chemical reaction involves changing mole coefficients. So the rule is the only thing I'm allowed to change is that whole number coefficient in front.
So, like, there's a blank NaCl. You can only change the number that goes in front. You cannot change subscripts. Those are untouchable. They're not
Right. Because it says if I do that, if I change the subscripts, then I'm actually changing what the actual reaction is.
Right. You're just like imagining it's not NaCl, it's Na2Cl, and oh, it's fine. Nope, that's not allowed.
Right, because then it's a different chemical. Which is different chemical, different equation.
Right.
Right. The other thing is when we're all said and done, we got to make sure that our coefficients are in their lowest terms. If I can divide them all by 2, then I got to do that.
And remember, we're only going to be changing the number for the number of moles of compounds out in front of the compound.
Right.
Nothing else.
Nothing else. No subscripts at all.
Okay. So let's see what we got.
Basic list of rules here.
Step 1, you got to list all the elements involved in the reaction.
Yep. I like to list them right underneath the arrow.
Yep, it's easy to do.
Whatever's on the left should be on the right.
Yep.
You know what I mean? And then we're going to go through and count them up.
Yep.
And this I do the same way too. Like, so if I have 3 oxygens on the left of that O, I'm going to write 3. And then I count how many are on the right. If there's 4, I put 4.
Yep. Then what you're going to do is you're going to pick one element that doesn't seem to balance out, and you're going to pick a number to put on that mole coefficient line, this one that I'm talking right there, that makes something balance.
Right.
You got to make a step in the right direction.
Correct. And then what you end up having to do is recount and repeat until all of our elements are balanced.
So I call this count, compare, coefficient, repeat. Count, compare, coefficient, repeat. Count, compare, coefficient, repeat. Say it.
Count, compare, coefficient, repeat.
How's that for alliteration?
Did it. And here's a trick.
Keep them polyatomic ions together if they are on both sides. So you got to look and see what didn't change.
Right.
Sometimes.
Right. And sometimes the NO3 on one side, if there's only one of them, won't have that parentheses, but it's still the polyatomic compared to the other one that's got 2 or 3 of them on the other side. And if I keep them together, there's just that many less steps I have with N's and O's to play with. I can keep that thing together as one.
Right. You keep it as a polyatomic ion because 99% of the time it stays as part of a single replacement or double replacement reaction.
Right.
And it doesn't break apart or do anything.
All right, let's try one.
So there's an example. You want me to do this one first, Mr.
If
Mills?
you want, go ahead.
Synthesis reaction. This is one of the 4 basic types of reactions that we're dealing with.
Nope, next video.
And this is how we gonna do it. So I've got this break down the middle, and what I'm gonna do is I'm gonna count the atoms of each type, and I see that I got a calcium, and I've got oxygen. That's on the left side. Now at the right side, I also have just calcium and oxygen. So I only have 2 elements involved. I don't need to list any more.
Good.
So now I'm going to count the atoms of each type of element involved. Calcium,
you see on the left.
I've got 1 of them.
Okay, and on the right.
I have 1 of them as well.
Beautiful. Oh, balanced. Oh, that's good.
The calcium part seems to be balanced. Let's see if the oxygen is.
Okay.
On the left-hand side of the arrow, I have O2, so there's 2 oxygen atoms. And on the right-hand side, I have O1. There's 1. So now I counted. Now I have to compare. Something doesn't match up.
Right, I'm going to say oxygen.
Yeah, you're right. Now I have to put a coefficient in on that blank line
Yeah.
so that I can get the oxygen to match up.
Well,
and I'm going to
multiply
pick
1 by to get the 2.
I'm going to pick a 2.
Beautiful.
Yeah. So put a 2 up there, and now you distribute.
Now this is what we talk about reevaluating, because now you made a change. You got to recount everything on the right hand side.
So now you got to count everything again. And on the right hand side, I no longer have 2 calciums because I'm distributing this. Remember?
Right. You no longer have 1.
I no have longer 1. Now I have 2.
It's okay.
I have 2 calciums now and 2 oxygens.
There you go.
So I counted.
So now oxygen's good.
Compare. Oxygen's good, but calcium's not.
So now what do
I got to put a coefficient in on the left side for calcium instead. I'm going to put a 2 there.
It worked last time.
Put a 2 there. Distribute it through. That means that's no longer 1, but it's 2 now. So I counted. I compare.
2, 2, 2, 2.
I'm good. And what goes on that blank line there, Mr. Mills?
That is a huge, huge piece.
This right here
is a 1.
It is a 1. It's implied. So there you go. Count, compare, coefficient, repeat.
If I were you,
Boom.
I would get in the habit of writing the 1.
Yes.
You don't need to be honest with you, but the reason why is that question always comes up. That's the part 1 question. When this chemical equation is properly balanced,
What is the coefficient that goes on this blank line?
right, and they'll ask you all the time on the oxygen.
Yeah, and it's usually 1. Maybe
Right.
it's 2 or 3 something.
Sure.
Let's move on. Let's do a decomposition.
All right, cool. My turn.
Your turn.
All right, so I'm going to start out again by listing my elements.
Diphosphorus pentoxide.
Thank you. I see phosphorus on the left and oxygen, and again on the right, that's all I see is phosphorus and oxygen. I'm going to start counting up my atoms. I have 2 phosphorus on the left. I have 1 on the right. Oxygen on the left, I have 5. And oxygen on the right, I have 2. Oh, this is going to be tricky. All right, so I could do the phosphorus first by putting a 2 in front of the one on the right, but that isn't going to help me with this oxygen at all.
No, it's not.
No, it's not.
Dry.
So I'm going to go actually tackle the oxygen first.
Right. And
So I got to come up with a way with 2 and 5 to get like a greatest common factor.
lowest
Common factor.
LCF.
Right.
Greatest common factor.
Right. I want to get the smallest number where they're multiples of.
Right.
And so I got to be honest with you, it's going to be 10.
5 and 2.
5 and 2 is 10.
Right.
So I'm going to have to multiply on the left-hand side, I'm going to have to multiply this 5 by a 2 to
he
get that
wants
up to
to
10.
get to 10 oxygens.
Right.
So
So
when
now
he distributes that
I'm
out,
going to distribute this out. I got to recount both. So I don't have 2 P's anymore. I have 4. And now I have 10 oxygens. Sweet. And now I can make some, right, now I can say I got 4 and 1, I got phosphorus, but let me stick with the oxygen for now. Now I'm going to make this a little bit bigger because that looks like an 8 right now. All right, so oxygen, 2 times what gets me to 10? 5 times 2 gets me to 10. Let me reevaluate. And I have 10 oxygen, so that's good. Check. And now I got to fix my phosphorus. So 1 times 4. 4. When I reevaluate that, that brings me to just at 4. And 4 and 4 when I reevaluate, we're good.
Dunzo.
Can I take those numbers and make them any smaller?
Nope, there are no greatest common factors.
So that one is
Dunsky. So synthesis, decomposition, let's do a single replacement with a polyatomic ion.
There you go.
You'll see that equation right there. Boom. All right, cool.
Now, before we start, polyatomic ions, what am I going to do?
Keep them together.
All right, good.
So I'm going to list up the elements and polyatomic ions that are at play here. I got Ag. I also have NO3. Notice on the left side, there's the NO3. On the right side, it's in parentheses. Easy to spot.
When it's in parentheses, it's a lot easier.
But really what I'm looking for is common chunks. I see that NO3 there. I see that NO3 there. I'm going to keep them together. I'm going to erase that so that we don't get confused. But that's why I'm writing NO3 as if it were an element in this
Right.
case.
We'll just treat it just like a regular element.
And then it looks like I got calcium involved as well.
Beautiful.
So now I am going to count.
Let's count them up.
AGs, one left side I got 1. NO3 group on the left side I got 1. Calcium on the left side I got 1. Reactant side 1, 1, 1.
Beautiful.
Product side, calcium, I've got 1. Nitrate, NO3s, I've got 2. Remember, this 2 is for the polyatomic ion
Whole
chunk.
parentheses.
And I've got 1 silver. So I counted, I'm going to compare. Silvers match, balanced. Nitrates don't match, not balanced. Calcium's matched, balanced. So what I have to do is I have to put a coefficient in on the line on the reactant side, the left-hand
It's going to
side.
change the NO3.
That's going to make the nitrate balance.
Right.
And so I need 2 of them on the left side. I'm going to put a 2 as my coefficient here.
And now I have to reevaluate.
Remember, I'm distributing this out when I am reevaluating here. So when I count again, AGs I've got 2 now. Nitrates I've got 2 now. Calcium I didn't touch, so it's the same.
There you go. Good.
Count, compare. Okay, AGs is not balanced, but nitrates is now.
Yep.
And so I have to put a coefficient in somewhere. Let's go and attack that AG on the product side. We'll put a 2 there, which means that I carry it through. I've got 2 silvers now. Compare. Okay, that balances. Silver balances. Nitrate balances. And wow, look at that. Calcium balances. So I have to put something on these other blank lines up here in the equation. 1.
I would do that.
And what this really means, it boils down to, and this is how it would read if it were a word sentence, 2 moles of silver nitrate combined with 1 mole of calcium metal and react to create 1 mole of calcium nitrate and 2 moles of silver metal. So as you can see, that long paragraph I just read or wrote or recited to you can be simplified in a chemical reaction, which is why we chemists write chemical reactions.
It is.
We don't want to have use all them words.
Yep.
We like symbols better.
Yeah. And one other reason why we have to put in those ones.
Because
There's one other.
it's implied.
Well, there's this one tricky question they ask us too sometimes.
What?
They say after this chemical equation is properly balanced, what is the sum of the coefficients?
Oh, gosh.
You
I
know
hate that
I know, but you know that 4 is going to be an answer because there's the 2 2s, and somebody's going to forget those
Was
ones.
and 6 is
So
truly the
4, 5, and 6 are going to be answer choices, and they're going to try and trip you on that one. They're going to try.
Ooh, you got many polyatomic.
Ooh, yeah, but I did this one earlier, so this one's actually not too hard. All right, let's do it though.
It looks terrifying.
Well, it does, but we'll find out it's actually pretty easy.
Yeah.
All right, so I'm going to do the same thing. I'm going to find out what I got. I'm going to list it underneath my arrow. So I see an Na. I see an NO3 in parentheses and another NO3 in parentheses. So let me keep that together like Mr. MoNaCo did. All right, and then I have a Ca. And then on both sides, I see again an SO4 and an SO4 in parentheses. So let me keep that together too. So in this case, I have 2 of these polyatomic ions. Okay, now we got to count them up. On the left, I got 1 Na. And on the right, I got 2. And on the left, I've got 1 NO3. And on the right, I got 2. And on the left, I got 1 calcium. And on the right, I've got 1 calcium.
Yay.
Ooh, that's good. And sulfate on the left, I've got 1 sulfate. And on the right, I've got 1 sulfate.
Oh.
So I see 2 things that I need to fix. So let me start with Na. I'll fix Na first. I need to multiply that 1 by a 2. So I have to go to the term that Na is in and multiply that term by 2. Because that's going to get me Na2 and NO3 2. Oh, look at that. Na2 and then NO3 goes to 2 also, and evaluate, and we are good. Done. Just like that.
No, you're not, sir. You have to draw in something on the blanks.
Righty.
Because if you got hit with that question, what is the sum of the mole coefficients? You'd have said 2 and been wrong.
And then, so there you go.
It's really 5
5
is the sum of the mole coefficients. Yeah.
So there you go. But there is a quick run through of balancing some
And a great example of how this process, if you follow it, makes a big, scary-looking equation not so bad. Not so bad. I mean, this thing looked terrifying at first. I thought it was going to be a nightmare to balance, but really, it was the simplest of all the 4 that we had done, because all you had to do was change 1 coefficient over on the reactant side, and boom, everything else played in.
And then while we're here, I want to give you just one little bit of advice from somebody that's balanced these things for too many years, right? If you see an element by itself like that in an equation, there's only 1, save that one for last.
Because you can put any whole number in front of it.
Any whole number here fixes it, and I'm only changing 1 thing. So I don't have to keep reevaluating, right? I don't keep going on and bouncing back and forth. So that's it. We're going to take some practice, guys. Be patient with some of them. If you screw up and you get into a spot where you back yourself into a corner, erase it all and start over.
We've actually got a simulation that should help conceptualize this process in another visual way.
And some practice.
And there's a ton of YouTube stuff out there for that practice. So, check out the related links. They might help you out if this didn't.
Sure.
Long video. Thanks for watching.